Good morning, everyone. In this presentation, I'm just going to give you a quick summary of my research in robotics for confined spaces. Before I start my presentation, I would like to thank all my current grad students, some of which are not just only from mechanical, but I have students also from electrical engineering, computer science, and also in the biomedical program. In my research group, we have three main goals, one of them being high speed, where we want to deploy robots such that they execute missions very fast. We want to deploy them inside confined spaces such that we can eliminate people from entering hazardous, potentially dangerous spaces. And we want robots to be able to make decisions as they perform the task without us having to give them a recipe on how to execute the mission. Examples of confined spaces include urban search and rescue. For example, perform operations inside collapsed buildings, mines, or beneath tree cover. Other examples of confined spaces exist in numerous industries, such as mining, oil and gas, construction, aerospace, and many other industries where people have to be deployed to work in hazardous, potentially dangerous conditions. In my research group, we currently have 7 research projects, some of them tackling high speed like transitional UAVs and supersonic drones, while others tackle confined spaces and full autonomy, such as multi-leg robots. However, because of the time limit, today I'm just gonna focus on highly maneuverable drones and also talk a little bit about our work in multi-leg systems, enable them to penetrate confined spaces. I will start by describing my work with drones for flight in confined spaces. In this area, we have developed different concepts with the purpose to perform acrobatic maneuvers at practically zero speed. And we have been focusing on transitional aircrafts as well as vertical takeoff and landing vehicles, where we use the tilting of the docks to maneuver and control the aircraft. Our most agile drone is the one that we call the Navigate. This aircraft uses tilt rotors, variable pitch propellers, and different other techniques to maneuver in space. Some of the acrobatic maneuvers that this aircraft can execute are pitch hover, like the one that you see in the figure there, which allows us to take off and land in highly sloped terrains up to maybe 75 degrees, depending on the conditions of the terrain. This aircraft is also being developed to take off and land from dynamic surfaces, such as the ones that you encounter when vessels are navigating on rough seas. Other acrobatic maneuvers include hover in roll, as well as hover inverted, and perform these maneuvers at low speeds. In this animation, you can see some of the flying characteristics of this aircraft, which enable to position the sensors at different positions and orientations around a specific subject of interest. To navigate this aircraft in confined spaces, we use the geometrical representation of the robot, the detailed representation of the environment, as you can see there in the figure, and the motion characteristics of the robot. Together, this information is put into a cost function that tries to maximize the distance between all the points in the environment and all the points that comprises the robot. All this information is used to control the aircraft, as I will show in this slide. First, using the onboard sensors of the aircraft, we generate a partial map of the terrain based on the perceived terrain. With the map of the terrain, we use the navigation technique that I explained in the previous slide to tell the robot how to maneuver to reach the target position in the three-dimensional space. With the three-dimensional map of the terrain and the navigation path, we use computational fluid dynamics to forecast the aerodynamic and ground effects that the aircraft will experience as it traverses the environment. With the three-dimensional path that the robot has to follow and the knowledge of the disturbances that the aircraft is going to experience, we compute the control commands to fly the aircraft. We have used different schemes to control this type of aircrafts, including backstepping control and artificial neural networks. So far, the best control approaches have been model predictive control, and now we're trying to use in the control to be able to cope with the coupling effects that the aircrafts have. In this slide, I just show some of the results of the navigation and control schemes in two-dimensional and three-dimensional spaces, where you can see that the algorithm really maneuvers the aircraft in tight spaces in order to reach the goal. As you can see in the left animation, the control and navigation tool are able to really quickly replan the path that the vehicle has to follow when a path is not possible. Due to the mechanical complexities of this aircraft that enables it to perform acrobatic maneuvers at slow speeds, the motions of the aircraft are tightly coupled. For example, when we want to perform a pitch hover maneuver, the vehicle will also tend to yaw and translate. Sometimes these coupling effects are beneficial, but sometimes they have devastating consequences. This is an area of research in which we're still working on, trying to decouple all of these motions to enable the vehicle to fly and perform maneuvers in even tighter spaces, as you can see in this slide. So in order to reduce the complexity of controlling a vehicle trying to follow a path error-free, we're defining what we call a highway approach, where the vehicle just has to be within a specific highway that takes into account the configuration space of the robot while maintaining a position and orientation. So we're developing control systems to enable the vehicle to stay within that specific highway that might be complex in shape and geometry, while still avoiding obstacles and eliminating ground and wall effects. Based on our work on rotorcraft, now we're aiming to increase the operational speed of this aircraft with something that we call a transitional UAV. For this, we're combining the characteristic equations to design rotorcrafts such as helicopters and quadrotors with the mathematical equations to design fixed-wing aircraft. By doing this, we have been able to formulate a set of mathematical equations that enable us to design transitional aircraft from scratch while managing the contradictions between the design parameters of rotorcraft and fixed-wing airplanes. Here I show you a sample experimental video of some of our preliminary work where the aircraft starts in a rotorcraft flight mode configuration and then by tilting the main rotors transitions to fixed wing flight. And of course, the reverse is possible. One of the aspects to see here is that this aircraft does not use any control surfaces such as ailerons and rudders to control the aircraft while in fixed wing mode. Now I am gonna switch gears and talk about my work on multi-legged and hybrid robots. Based on the three goals of my research lab, we have been developing diverse mechanisms for humanoid robots to operate in confined spaces. Some of the techniques include whole body planning mechanisms and multi-contact control approaches. I have also been working in hybrid multi-leg systems, which I define as robots having diverse locomotion modalities that enables them to walk, climb, roll, swim, and maybe one day in the future they will be able to fly. As you can see from this image, these robots are also able to reconfigure to adapt different geometrical states, enable them to walk on rough terrain, climb on vertical pipelines, climb ladders, and perform acrobatic maneuvers. One of our visions is to enable these robots to perform parkour type motions, which we believe will enable them to solve the challenges that they may face when penetrating confined chaotic spaces. This work includes developing techniques that will facilitate these robots to switch between locomotion styles, plan their body motions, and reconfigure based on the perceived geometrical features of the environment. One of our techniques is imitating animal behaviors that can be used as a general approach to learn controllers for a variety of skills. Our framework consists of three components. First, given motion data from an animal, we retarget the motion of the animal's morphology to the robot's morphology. Next, we apply reinforcement learning to train a control policy to imitate the motion in simulation. Finally, the policy is transferred from simulation to a real robot via a domain adaptation technique and solving the real to sim problem encountered in other approaches. Real world animals will often have a different geometrical morphology than a robot, including different power and motion characteristics. Therefore, before the robot can imitate the animal's motion, the motion is first retargeted to the robot. To retarget a motion, we first specify key points on the animal's body, such as feet, hips, and shoulders. Corresponding key points are then specified on the robot's body. Key points are then extracted from each frame of the motion and mapped to corresponding key points on the robot. Inverse kinematics is then used to compute a kinematic pose trajectory for the robot that tracks the key points. Once the motion has been retargeted, reinforcement learning is used to train a policy to imitate the motion in simulation. The policies are trained using a reward function that encourages the policy to minimize the pose error between the reference motion and the simulated robot. Our goal is to use the same reward function to learn all the skills. After training in simulation, domain adaptation is applied to transfer the learned policy to a real robot. To facilitate transfer to the real world, we randomize the dynamics during training. The dynamic parameters include joint compliance, inertias, masses, terrain compliance and friction, as well as the range of motion of the motors. Although our past work has provided solutions to diverse aspects, there are significant challenges that remain to be solved. At the moment, we are developing active compliant joint mechanisms imitating how humans change the compliance of their joints based on the task and the terrain properties. This will enable robots to perform maneuvers at higher speeds, cope with diverse terrain complexities, and locomote on compliant rough terrains, as you can see in these images. Adding compliance has diverse advantages, such as cope with unexpected environmental changes, reduce robot damage, and reduce energy consumption, among many others. Finally, I would like to thank all the people with whom I have collaborated. This slide provides the list of the people with whom I have collaborated in the past 3-4 years from diverse departments, universities, and people with whom I have recently submitted research proposals. Thank you for your attention.